Ever tried waiting for a video to generate? It's like watching paint dry in slow motion. But what if I told you there's a way to speed it up without losing any quality? Enter Sparse VideoGen, the superhero of video diffusion models. Here's the deal. Video generation is slow because of 3D full attention. It's like trying to track every single pixel in every single frame. But guess what? Not all pixels are created equal. Some care about what's happening right now, that's spatial attention, while others care about how things move over time, that's temporal attention. Sparse VideoGen is like a smart detective. It figures out which pixels need attention and skips the rest. As a result, videos render 2 times faster, and they still look amazing. Ready to see how it works? Let's dive in.
Let's talk about video generation. Diffusion transformers are powerful. They can create stunning videos, but there's a catch. They're painfully slow. We're talking several minutes just to generate a few seconds of video. Why? The culprit is 3D full attention, which has quadratic complexity. As video models scale up, this becomes a massive bottleneck. Enter Sparse VideoGen, SVG. This method speeds things up without any extra training, by leveraging the inherent sparsity in how attention works. Here's the key insight. Attention heads in these models naturally split into 2 types. Some focus on spatial relationships within the same frame, while others handle temporal connections across different frames. SVG profiles these patterns dynamically and applies optimizations based on whether spatial or temporal attention is dominant. By rearranging memory layouts and using custom GPU kernels, SVG achieves over 2 times faster inference while keeping video quality intact. To prove it works, they tested SVG on 2 big video models, Cog Video X and Haocheng Video. The results are striking. For image-to-video generation, dense attention took 9 minutes, while SVG cut it down to 4 minutes. For text-to-video, dense attention needed 38 minutes, but SVG did it in just 16 minutes, without losing quality. Visual comparisons show that dense attention often leads to blurring and temporal inconsistencies, while SVG maintains sharp details and smooth motion. This sets the stage for the rest of the paper. We've got the problem, slow video generation, the key observation, sparsity in attention, the solution, SVG, and its impact, 2 times speed up without quality loss. Next, we'll dive into how this sparsity profiling works and how hardware optimizations come into play. So why is attention such a bottleneck? Let's break it down. In video diffusion models, the longer the video and the higher the resolution, the more dominant attention becomes. Take a 5-second video generated by Haocheng Video on an NVIDIA A100 GPU. It takes almost an hour, and 3D full attention alone consumes over 80% of that time. Look at figure 2 here. It shows how attention scales with context length. At 17K tokens, attention already takes up 51% of the total computation time. By 120K tokens, it crosses 80%. This quadratic growth in complexity is what makes video generation so expensive. But here's the thing. Attention isn't as dense as it seems. Just like in large language models, many tokens contribute little to the final output. In text models, filtering out unnecessary tokens saves huge amounts of computation. But video transformers are trickier. Their sparsity patterns are very different. That's where Sparse VideoGen, SVG, comes in. Instead of applying full attention everywhere, SVG profiles sparsity patterns dynamically and reduces computation in both spatial and temporal dimensions. How? First, it randomly samples a small portion of tokens per head, figures out whether they fall into a spatial or temporal pattern, and applies different sparsity strategies accordingly. Second, it reorders memory layouts to make sparsity easier to compute on hardware. To make this work efficiently on modern GPUs, they implement customized kernels using Triton and FlashInfer. Tests on Cog Video X and Haocheng Video show that SVG achieves a 2.3 times speedup while maintaining high-quality results. They even show that applying additional sparsity beyond what SVG predicts hurts quality, meaning the method has found an optimal balance between efficiency and fidelity. So, what's the takeaway? Attention is the bottleneck in video generation. Video models have 2 distinct sparsity patterns, spatial and temporal, and SVG speeds up generation without hurting quality by profiling and optimizing these patterns. Now let's dig into how attention works in video models. It's not the same as in text models. Instead of looking at word relationships, Video diffusion models need to handle both spatial and temporal attention at the same time. Check out Figure 3 for a clear visualization. Video attention splits into two types. Spatial attention, shown in red, focuses on relationships inside a single frame. Imagine looking at a single image and making sure everything is consistent. This ensures that objects and textures are generated correctly. Meanwhile, temporal attention, green, tracks the same spots across multiple frames. This is crucial for keeping things like motion and object positions coherent over time. The diagrams make this easy to see. The spatial attention map, B, shows that attention stays mostly inside each frame, meaning the model doesn't worry about past or future frames here. In contrast, the temporal attention map, D, highlights how temporal attention works across time, ensuring the same parts of an object remain in place across multiple frames. Finally, look at Figure 3, E, which visualizes an actual example. A video of a hot air balloon moving through the sky. The red lines, spatial, show how attention links different parts of a single frame, ensuring sharp details. Meanwhile, the green lines, temporal, connect the same balloon position across all frames, preventing flickering or sudden changes. This breakdown is essential because Sparse VideoGen, SVG, optimizes both types of attention differently. Instead of applying full attention everywhere, SVG analyzes the scene dynamically and reduces unnecessary computation for both spatial and temporal cases. This means the model can run much faster without sacrificing video quality. The page wraps up by comparing this to previous work in efficient transformers and low-bit quantization. Some models reduce attention using quantization or token selection, but these methods don't take video sparsity into account. SVG is unique because it leverages spatial and temporal redundancy, specifically for video generation, making it different from optimizations used in text-based transformers. Traditional video transformers treat all attention equally, but that's inefficient. Sparse VideoGen, SVG, fixes this by splitting attention heads into spatial and temporal types and applying different optimizations to each. Take a look at Figure 4. Instead of predefining which heads are spatial or temporal, SVG profiles them dynamically. It does this by sampling a small portion of queries and testing both spatial and temporal attention on them. The method that produces results closest to full attention with the least error is chosen. This ensures that SVG stays adaptive without requiring extra training. Spatial heads focus on nearby tokens within the same frame, ensuring local details remain sharp. Temporal heads, on the other hand, track the same positions across frames, keeping object motion and consistency intact. SVG uses this knowledge to selectively process only important tokens, skipping unnecessary computations. The best part? Sparse attention achieves lossless accuracy. Experiments on Cog Video X and Hunyuan Video show that sparse patterns don't degrade video quality. In fact, they maintain a peak signal-to-noise ratio, PSNR, of 29, meaning the visual clarity remains high even when using selective attention. Beyond accuracy, this method also delivers massive speed improvements. Instead of performing full attention on every token, SVG reduces the number of comparisons significantly by applying sparsity rules. The paper introduces formulas that quantify these savings, showing that sparse attention dramatically lowers computational cost without compromising on performance. The key insight here? SVG's selective attention is fast, efficient, and adaptive. Unlike previous methods that assume fixed sparsity, SVG learns on the fly which type of attention works best, making it an ideal approach for video generation. Attention heads aren't all the same. Some focus on spatial details inside a single frame, while others track motion across time. But how do we know which head should do what? That's where online profiling comes in. Instead of assuming fixed sparsity, SVG dynamically figures it out using an online profiling strategy. Here's how it works. Take a small sample of queries and test them with both spatial and temporal attention. Then, compare the results to full attention using mean squared errors. The approach that gives the closest results wins, and SVG assigns that attention head accordingly. This means SVG doesn't need retraining. It learns on the fly. But there's a catch. Temporal attention is not hardware-friendly. The problem is that tokens for the same position across frames are scattered all over memory. GPUs, like NVIDIA's Tensor Core, work best when processing contiguous blocks of data, but temporal attention's default layout is fragmented, slowing things down. Look at Figure 5 to see how SVG fixes this. The key is rearranging memory layouts. Instead of keeping tokens scattered, SVG transforms the data into a frame major format, where tokens from the same position in different frames are stored together. This makes it easier for GPUs to process them in bulk, unlocking real speed improvements. With this method, SVG achieves up to 30% sparsity while maintaining high video quality. Tests on Cog Video X show that it retains a peak signal-to-noise ratio of nearly 30, meaning the generated videos still look sharp and clean. This is a crucial step, because sparsity alone doesn't guarantee speedup. Efficient memory layouts matter just as much. The takeaway? Real-world acceleration depends not just on skipping computations, but also on making sure GPUs can process the remaining ones efficiently. Measuring how well a video generation model performs isn't just about speed. It's about balancing quality and efficiency. Let's dive into the benchmarking results and see how Sparse VideoGen, SVG, stacks up against other models. Check out Table 1. It compares multiple methods across key metrics. First, we have quality scores like PSNR, SSIM, and LPIPS, which measure how visually accurate and perceptually similar the generated videos are. SVG leads across the board, achieving the highest PSNR and SSIM while keeping LPIPS low. The bench scores further confirm that SVG preserves temporal and spatial coherence better than other approaches. But what about speed? This is where SVG really shines. It achieves a 2.28 times to 2.33 times speedup compared to standard full attention methods, while other baselines like DIT-Fast-Atten, spatial only, and Minference also attempt to optimize performance. They either sacrifice too much quality or fail to match SVG's computational efficiency. SVG, on the other hand, maintains high visual quality while using fewer floating point operations. The page also touches on additional optimizations that help make SVG practical. By fine-tuning QK norm and rope, or rotary position embedding, functions, the system reduces memory bottlenecks and achieves a 5 times speedup in key components. Another tweak involves FP8 quantization, which speeds up inference by another 1.3 times with minimal quality loss. Finally, the paper outlines how SVG was tested. The models were evaluated on Cog Video X and Hunyuan video datasets, using VBench and human perceptual metrics to ensure real-world usability. These experiments confirm that SVG isn't just a theoretical improvement. It works in practice, making video diffusion transformers significantly faster without compromising quality. What does SVG's video generation actually look like? Take a look at Figure 6 for a clear side-by-side comparison with standard dense attention models. It covers 4 different scenarios: minor and major scene changes, rare object interactions, and frequent motion. No matter the case, SVG's results match the originals while being much faster to generate. Speed isn't just about raw numbers, it's about where the improvements come from. Jets. That's where Figure 7 breaks things down. Hunyuan Video's full inference time originally took 2,253 seconds. That's nearly 38 minutes for just a 5.3-second video. But SVG cuts this time down to 968 seconds, achieving a 2.33 times speedup. The bar chart shows how different optimizations contribute. Baseline performance without optimization is slow. Efficient kernel design speeds things up. Sparse attention reduces unnecessary computations. Every name. FP8 quantization pushes efficiency even further. Now, check out Table 2. It zooms in on specific speed improvements from QK norm and rope optimizations. QK norm gives a 7.47 times boost, while rope nearly quadruples performance at 16.47 times speedup. These optimizations work by making tensor computations more GPU-friendly, allowing video diffusion transformers to run significantly faster without hurting quality. The takeaway? SVG isn't just faster, it's smart about where it cuts computation. It keeps attention sparse in the right places, reorganizes memory for better GPU efficiency, and applies FP8 quantization to squeeze out even more performance. The results prove that it can match full attention models in quality while being much more efficient. Speed matters, but not if it comes at the cost of video quality. That's where SVG's online profiling strategy comes in. Instead of wasting computation on every token, it analyzes a small subset and determines the best sparse pattern dynamically. Take a look at Table 3. Profiling only 1% of the tokens achieves nearly identical video quality as profiling 100%, with a PSNR of 31.1 compared to 31.3. That's a huge reduction in computation with almost no drop in quality. Now check out Figure 8. The problem with naive sparse attention is that it's inefficient for GPUs. SVG fixes this by optimizing memory layouts for temporal attention, ensuring tokens are stored contiguously. The result? A 1.7 times speedup over naive sparse attention, bringing latency close to the theoretical limit. Finally, Table 4 dives into how different sparsity levels affect video quality. Even at a 31% sparsity ratio, SVG achieves an LPIPS of 0.154, meaning the generated videos remain perceptually similar to full attention models. The conclusion is clear. SVG makes video generation faster without sacrificing quality. It carefully selects where to apply sparsity, reorganizes attention for efficient GPU execution, and balances speed with accuracy. This combination makes it a practical and scalable approach for real-world video diffusion models. Thanks for joining us today. Happy learning and stretching together.